Thank you so much for having me. Yeah, I'm really excited to talk about this recent work on parallel algorithms for finding Matroid bases. And so to start, okay, I can imagine that there are some of you who aren't so familiar with Matroids. So at least for the first couple minutes, I'm just going to kind of slowly go through the definition of Matroids, give you some examples to work with in your head, so you can hopefully follow the rest of the talk. And so a Matroid, I'm going to denote it just by the letter M throughout this talk today. And it's specified by two things. Right, so a Matroid M, it consists of the set E and a set I. The set E is this so-called ground set, and it just consists of n arbitrary elements. And the set I is what we call the set of independent sets. And so I is a set of subsets of E. And importantly, when we talk about Matroids, this set I satisfies many convenient structural properties. So in particular, the set I satisfies this hereditary property, which says that if you have some set S, again, which S is a subset of your ground set, if S is in your set I, then for any subset S prime contained in S, S prime is also contained in I. It's an element of I. Right, so what this means is that your set of independent sets I is downward closed. And now the second property that we have in Matroids is what we call the exchange property. And what this is telling you is that if you have two sets S and T, both of which are in I, I'll sometimes say this as S and T are both independent, but that your set S is bigger than your set T, then it must be the case that there's some element you can take from S and give to T such that T with this new element is still independent. Right? And it might seem a little bit arbitrary that these are the definitions that we're imposing on this set system to call it a Matroid. But as we'll see on the next couple of slides, there's actually very many concrete examples where this notion of independence does satisfy these convenient properties. Right, so for instance, maybe the most canonical example of a Matroid, and a very good example to keep in mind, is something called a graphic Matroid. Right, so here you're given a graph G with vertices V and edges E, and we'll let the set of edges E be the ground set of our Matroid. And right, so now we need to define what are the independent sets in this graphic Matroid. And so we say that a subset S of edges is independent if and only if S contains no cycles. Right, and so I won't prove to you that this satisfies the axioms of being a Matroid. But for instance, you could see that this certainly satisfies this downward closure property. Right, because if you have a set of edges S which has no cycles, well, then it's also the case that any subset of S also doesn't contain any cycles. And now another example of a Matroid is something called a linear Matroid. Right, so here, again, you're given your ground set E. But now your ground set E is going to be a set of n vectors. And as before, okay, we need to define what does it mean for a set to be independent in this Matroid. And so we'll say that a set S, which is now just a subset of these vectors, we'll say that S is independent if and only if it corresponds to a linearly independent set of vectors. And again, I won't go through all these conditions prove to you that it is indeed a Matroid. But again, at least the downward closure property should be clear to you, right? If you have a set of independent, linearly independent vectors, then any subset of those vectors is also linearly independent. There's also some even more basic examples of Matroids, and we'll even be talking about these later in the talk today. The first of these is something called a uniform Matroid. So again, here you're just given some set E, which is n arbitrary elements. But now you're also given a budget parameter B. And we'll just define that a set S, which is a subset of these n elements, we'll say that it's independent if and only if it has at most B elements. Right? So it's independent if and only if magnitude S is less than or equal to B. And there's even one further generalization of this to something called a partition Matroid. And this will feature prominently in the second half of the talk. So here you're given a set of elements E, just again, those n arbitrary elements. And now what we do is we break up this set of elements E into a bunch of different pieces, P1, P2, all the way up to Pk. And for each one of these pieces, we assign a budget parameter Bi. And now we'll say that a set S is independent if and only if S intersect Pi is less than or equal to Bi. Right? Equivalently, S has at most Bi elements from each part Pi. Right? And so the way to think about this is that it's basically like a disjoint union a bunch of like uniform matroids. Right? So you take one uniform matroid on part P1, and then another on P2, P3, and so on. And your query is independent, or your set S is independent, if and only if you don't exceed the budgets of any single one of these parts. Great. And so this is the kind of examples of matroids that hopefully gives you some intuition for what the structure looks like. But today we're not just going to be talking about like matroids and what do they look like. We're actually going to care about very specific notions of structures that emerge in the study of matroids. And so for this, I need to define a couple notions. And again, they'll appear very abstract at first. But then on the next couple of slides, I'll revisit these notions in the context of those examples that we just looked at. So hopefully you'll get some footing on what do these quantities exactly correspond to. So the first structure we're going to look at is something called a circuit. So again, here you're given your matroid M. It has a ground set E, has your independent sets I. A circuit is just a subset of elements which is a minimal dependent set. And so what does this mean? It means you have a subset of elements C such that on its own, it is not independent, right? It's not in your set I. But that if you take any single element from your circuit C and you throw it away, now it becomes independent. Right? So on its own, it's dependent, but if you throw anything out from this set of elements, it becomes independent. A basis is kind of the opposite on this side of the spectrum. Right? So again, you're given a matroid M. A basis is a subset of elements which is a maximal independent set. Right? So what does this mean? On its own, the set B is independent, but any other element that you try to add to the set B will make that set become dependent. And the last notion that I'm going to mention is this thing of notion of a rank of a matroid. So again, here you're given your matroid, and you're looking at a subset S of elements in your matroid. The rank is just the size, the maximum size of an independent set contained in S. Right? Equivalently, it's the size of any basis of that set of elements S. Right? Okay, these might appear very abstract at first, but let's revisit these examples that we just saw and see what these notions correspond to. Right, so the first example we looked at was this graphic matroid. Right, so you're given a graph G with vertices V, edges E. The matroid is defined over the edges of the graph. And we said that a set S of edges is independent if and only if it contains no cycles. Right, okay, so then what is a basis? Right? A basis is a maximal independent set. So it's a maximal set of edges that does not contain any cycles. Right, and so this is exactly then a spanning tree of your graph tree. Or maybe more carefully, it's like a spanning forest. Maybe the graph wasn't connected. Right? At the same time, you can ask, what is a circuit? A circuit is a minimal dependent set. Right? So what's the smallest set of elements which is not independent? Well, okay, we kind of defined it's independent if and only if it contains no cycles. So like the smallest dependent structure would then necessarily just be a single cycle on its own. Right, and we can also revisit these notions in the context of the linear matroid. Again, here your ground set is a set of vectors. And we say that a subset S of them is independent if and only if that set of vectors is linearly independent. So a basis here, again, a maximal independent set, well, it's just a maximal linearly independent set of vectors. That's exactly like the canonical notion of like a basis of a linear space. Right? That's kind of the motivation for this term basis of a matroid. A circuit is a little bit less well-defined in this linear space. It's somehow, it's a linearly dependent set of vectors such that if you dropped any single one of these vectors, now all of a sudden the rest of those vectors would become linearly independent. It's not really a notion that we use frequently in the study of linear spaces, but it's still well-defined in this setting. And again, we have these basic examples of like the uniform matroid. Again, so here you had your set of elements. A set was independent if and only if it has size at most B. So here, okay, what is a maximal independent set? Well, okay, kind of by definition, it's just B elements. A circuit is a minimal dependent set. Okay, the smallest dependent set will just have exactly B plus 1 elements, right? There's nothing mysterious happening here. Yeah, question?
The other definition you gave was for rank. But you haven't been talking about rank anymore. Is rank in cases?
So yeah, I guess rank will just, that's a good point. So let's say, like, in this example, right, like, what's the rank? So it's going to be the size of a spanning tree of your graph G. It's a bit weird. It'll be like n, the number of vertices minus the number of connected components. Yeah, that's a good point. In a linear matroid, the rank coincides exactly with, yeah, just the rank of the space. So yeah, linear matroids are a very good example to keep in mind for when you're trying to think of, like, what properties of a matroid hold or what's the definition of something. Usually it coincides with what you would just use in the linear matroid. Here, again, the rank would just be exactly b, but yeah, exactly. Perfect. And so then we also have this last example of the partition matroid. Again, it's like the disjoint union of these uniform matroids. And yeah, it was independent if and only if you didn't exceed the budget in each one of these parts. And so I don't know if it's exactly clear to see, but a basis, right, it's a maximal independent set. It'll just mean that you exactly meet the budget in each one of these parts, right? So S intersect PI is exactly BI. A circuit, a minimal dependent set, just means in a single one of these parts, you're going to exceed the budget by 1. That's like the smallest possible dependent set you can have. Perfect. Are there any questions about this? We're going to use some of these notions going forward, but hopefully at least you have some intuition of, what do matroids look like. So one important thing I want to mention is that in these examples we looked at, in particular in the graphic matroid, in the linear matroid, this notion of a basis turned out to be a very important object for us to look at, right? So in graphs, a basis of the graphic matroid was a spanning tree, right? Which is something that we care about a lot when we work with algorithms. In the linear matroid, this notion of a basis coincided exactly with a basis of a linear space, which again is something that we care about a lot in the algorithms literature. Like, how do we compute this object efficiently? And so in general, finding a matroid basis is a very common generalization and very elegant generalization of lots of fundamental tasks in combinatorial optimization that we do care about. And not only this, but it turns out to be a very important subroutine in many other tasks. And so I won't really define these, but if you're interested, it turns out that you use this matroid basis finding in this problem of matroid intersection, and also in a lot of optimization problems that are subject to matroid constraints. And that's just to say, so this notion of finding a matroid basis is a very ubiquitous problem in combinatorial optimization. And so today, when we're going to talk about algorithms which find a matroid basis, we need to be careful how exactly we formulate this problem. And there's one key subtlety, which is the cause of this. And that's that when you're talking about a matroid, right, we fix this parameter n to mean the number of elements in the ground set of the matroid. But it turns out that once you fix this number n, the number of possible matroids grows super exponentially in this size of the ground set. Right, what does this mean? If you have a ground set of size n, the number of matroids is growing as 2 to the 2 to the n. And so when you want an algorithm which is finding a basis of a matroid, you can't write down the entire matroid for the algorithm to use, because it will be exponentially long on your input tape. Right? We cannot hope to describe general matroids in a succinct manner. And so today, when we're talking about how do we find matroid bases, how do we design general algorithms for finding matroid bases, we're going to rely on something called oracle access to the matroid. And so in particular, throughout this talk today, we're going to assume the most basic form of access to the underlying matroid. And this is something called independence oracle access. Right? What does this mean? Again, you're given the ground set E of your matroid. And what you get to do is you get to specify a subset S of your ground set and send these over to the oracle. And it will just tell you whether or not this set is independent. Right? It tells you whether or not this set S is in the set I. And is everyone clear with this? Right? So this is the type of access that we're going to be using throughout the talk today. And so I claim that even with this very rudimentary form of access to the matroid, I claim that it's already very easy to find a matroid basis. to like algorithmically find a basis of your Matroid. And not only that, I claim it's easy just with the most basic greedy algorithm that you can think of. And so we're even going to step through this algorithm and see how it works. Because again, it'll build very important intuition as we go into these more intricate algorithms later in the talk. Right, so how does this work? We're going to fix this set B, which is going to be the independent set that we've chosen so far. Right, and the goal is that by the time you get to the end of the algorithm, the set B should become a basis of your Matroid M. The second thing is we're going to fix a buffer of remaining elements, which I'm just going to denote by F. Right, so this is like the set of all the remaining elements that we need to process in the Matroid. And so to start, the set B is the empty set, right, because we haven't found any independent elements yet. And then the buffer F is just all the remaining elements in the Matroid. And now the algorithm is super simple. While the buffer is not empty, you're just going to take the next element E from your buffer and check if you can add it to your candidate basis B. Right, so what does that mean? You're going to query the independence oracle with your current candidate basis B along with this new element E. And so if this query is independent, right, it's telling you that you can add the element E to your basis while retaining independence. And otherwise, OK, maybe it returns 0. Then you're just going to throw the element away. Right, so you're just greedily checking, can I add this element to the basis? If the answer is yes, then I'll add it. If the answer is no, then I'll just throw the element away. And the claim is that at the end of this entire procedure, your set B is indeed a basis of the Matroid. And so does anyone see why this is the case? Alice?
I guess, like at the moment at which you're trying to add E, you would have made it dependent, but you didn't. And that superset of a dependent set is still a dependent set, so the same thing was for the final set you end with.
Yeah, perfect. Great. So let me summarize what he said. What he's basically saying is it's like more or less definitional. Right? So what is a basis? A basis is a maximal independent set. And so at the end of this algorithm, the set B is certainly independent, right? So we only ever added elements when it was still independent. And so all that you need to show is that it's indeed maximal. But this is more or less trivial, right? Because for every element that you didn't add to your set B, you have like a certificate of why you didn't add it, which is that I tried to add it and it became dependent. Yeah, is there a question?
Yeah. Does that include elements that are in
How do you mean?
Like, will B have any redundancy when basis?
No. So when I say basis, there can't be any redundancy. Yeah, it has to be only independent elements, nothing, no redundancy. Yeah, perfect. Great. OK, and so this is like the algorithm we just saw, right? It's a super basic, greedy algorithm. It finds you a basis of the Matroid. But there's one sense in which it's a little bit unsatisfying, right? And that's that it's a very sequential algorithm. Right? What you did is you took one element at a time, and you checked if you could add it to the basis that you're building. And so what we're going to talk about today is the parallel complexity of finding Matroid bases. If you'll wait for them to go by before I... Yeah. Wait, sorry, what do you say? Yeah.
Are we going to be mostly concerned with finding one basis? Or?
Yeah, great. So we're going to be concerned with just finding one basis of the Matroid. Yeah. OK, perfect. Now I'll pick up. So again, this algorithm that we just looked at, it was a little bit unsatisfying because it was a very sequential algorithm. Right? At every step of the algorithm, you were like just checking one additional element. And then your future queries and like your future decisions depended on what you did with this single element. And so what we're going to think about today is whether you can make parallel algorithms for this process. Right? So we're going to talk about how many adaptive rounds of computation you need in order to find a basis of an arbitrary Matroid. And so in a little bit more detail, like what's the class of algorithms we're looking at? So in each round of the algorithm, you're allowed to make a batch of a polynomial number of these independence queries. And now between rounds, the algorithm gets to read all the answers to this batch of queries, and then adaptively decide, OK, what's the batch of queries that I'm going to make in the next round of computation? right? And so the goal is to find a basis in a small number of these adaptive rounds of queries. And right, so in particular, this algorithm that we just looked at, the greedy algorithm, it made n adaptive rounds of queries, where in each round, there was exactly one query. Right? And so what we're asking is, OK, we're going to bump up the number of queries per round. Instead of being one query per round, you're allowed to make a polynomial number of queries per round. But you're asking whether you can reduce this number of adaptive rounds of queries. Right? Oh, yeah, question?
So when you increase the number of queries, you check all the new elements that you get from all those multiple queries from the basis with respect to form a linear independent set with respect to this independent set that you already have, or do you check one by one?
Sorry, you mean for the greedy algorithm?
Yes.
We were checking just one by one. Yeah.
Also,
And the reason, so you can check every element, right? Can you add it to the basis? But if the answer is yes, there's no guarantee that you can add all of them at the same time. It's only telling you that you can add one at a time. Does that answer your question? A little bit? OK. Perfect. OK, and so as we alluded to before the talk started, right, it turns out this question of asking, what is the parallel complexity of finding a Matroid basis? It's a question first posed by Richard Karp, Ellie, and then Avi Vigdersen in 1985. Right, they exactly posed this question of what is the round complexity of finding a Matroid basis when you're only given access via these like independence oracle queries. And so I'll probably refer to this paper as KUW. I'm just going to be reading off the initials of the last name. But so already in 1985, in this KUW paper, they showed surprising results that this task of trying to find a Matroid basis in parallel, you can actually find non-trivial parallel algorithms, right? You can get a round complexity, which is just order square root n. Moreover, it's still a deterministic algorithm, which you can use to find a basis of any Matroid using just a polynomial number of independence queries per round. Right, so the greedy algorithm was n rounds. And here, they're already getting all the way down to order square root n rounds for finding this Matroid basis with only a polynomial number of queries. Right, so it's like a very big improvement. And I think that this algorithm has like really nice insights about like how does structure in Matroids work. And so we're actually going to go through this algorithm together. Because again, it'll be very important intuition for us to have as we go on. And so I'll even try to reuse some of this notation that we had from the greedy algorithm. And so the way it'll work is just like the greedy algorithm. It's going to maintain these two sets B, which is your candidate basis, and F, which is your buffer of elements that you still need to process. And so just as before, your candidate basis is empty at the start, and your buffer F is full of all the elements in the ground set at the beginning. And so the key idea is, right, OK, if you think about what exactly is the greedy algorithm doing, well, somehow the greedy algorithm, it was just processing one element in each round of computation. And so we're going to somehow try to bump this up. We're going to somehow try to make process square root n elements simultaneously in each round of computation. But we're going to do so while maintaining two key invariants. The first is that your set B should always be an independent set. That's the same thing that we were asking for in the greedy algorithm. And the second thing is that we're going to say rank of F union B should equal rank of E. And so what does that exactly mean? Like, think about when the algorithm is done, F will just be the empty set. Right? So it's telling you then that rank of B equals rank of E. That's basically telling you that your basis needs to be full, right? It needs to have, be like the maximum possible dimension that it can be. Yeah, question?
Are you given rank of E, or is there a way to compute rank of E without computing B?
Great. So if you knew the rank, or in general, if you had a way to compute the rank of any arbitrary subset, then it's actually a very easy problem to find the basis. So you can't really assume that you know the rank of E. And yeah, somehow it's actually morally equivalent to like finding a basis. Great.
Oh, so like if you had the rank oracle, this whole
Rank oracle is just one round. Yeah. And so that's also one way to understand what KUW is asking. They're saying, what is the round complexity of using like independence oracle access to compute rank? These are like essentially the same question as the basis finding. Yeah, question?
think for the naive solution, it also satisfies this condition already.
Yes, the naive one will do that. The main difference is that now it's going to be like, you're going to do it while you're doing like square root n elements per round instead of just one. Yeah, perfect. OK, so how does this algorithm look? So let's say that these are the n elements in the Matroid, right? E1, E2, all the way up to En. Right, if your goal is to get a square root n round algorithm, a very natural first step is just to break everything up into square root n groups of size square root n. And that turns out to be the right intuition to have. So what we're going to do is we're going to take our n elements, and we're going to bucket them into these buckets of size square root n. So here's the first bucket, and that second bucket will have square root n all the way up to the last bucket, which has e sub n minus square root n plus 1 to the last element e sub n. And now what does the algorithm do? Within each one of these buckets, right, each one of these groups, it's going to query all prefixes of elements. And so, OK, what exactly does this mean? Let's zoom in on one of these buckets and take a look. So here I've just blown up the first bucket, E1 through E square root n. And so when I say query all prefixes, what I mean is that you first make a query to the independence oracle, which is just the element E1. Then you make another query, which is element E1 and E2. Then you make another, which is E1, E2, E3, E1, E2, E3, E4, and so on. Right? So you make one for every single possible prefix. So you'll make square root n queries in this prefix round. And now there's two cases for us to consider. Right? You've queried every prefix, and now you get your responses from the oracle. Case 1 says, imagine that this last query, right, when you queried all square root n elements, imagine that that was independent. Right? That's actually very good news. Right? It's very easy. Right? What it's telling you is that all of a sudden you just found square root n independent elements in one round of queries. So all I'm going to do is I'm going to take those square root n elements and add them to our candidate basis B. Right? Like you found these independent elements, you can add them to your basis. Now your basis increases in size by square root n. That's great progress if we're targeting a square root n round algorithm. Good. Case 2 is a little bit more subtle. So what's happening in case 2, it must be the case that your last query is not independent. Right? Because case 1 said the last query is independent. Now it's saying the last query is dependent. And so what this is telling you now is that you have this sequence of queries starting from the very beginning. And so your first query was independent, say. Your second query was independent. And it kept on being independent. And then at some point, it changed from being independent to being dependent. Right? When you queried all your prefixes, there was a moment in time at which the queries changed from being independent to dependent. And so what I claim is that you can find the first element, E sub j, such that E1 through EJ was dependent. And you can throw away this element EJ while still preserving the existence of a basis. Right? So in this example, right, this query was independent, this query was independent, this query was dependent. So what we're going to do is we're going to throw this third element away. And does anyone see why this is valid? Exactly, yeah. And that's good intuition to have, right? Like, and maybe one, like, let's do like a concrete example maybe for some, there's another.
So when you say throw away EJ, do you just throw away EJ or do you throw EJ and everything after?
Only EJ, only element EJ, yeah. Right, so it feels a lot like the greedy algorithm. And there's something important that we're learning, right, when we're doing this process. So let's imagine that these were vectors for a second, right? Like maybe vectors are like the easiest case to build intuition. And so what this case is telling you is that, OK, vector v1 is linearly independent on its own. Vectors v1 and v2 are linearly independent on their own. But now vectors v1, v2, and v3, are linearly dependent. And the only way that's possible is if V3 is in the span of V1 and V2. Right? So keeping V1 and V2, you're kind of guaranteeing that you're like not losing any dimension of your space, right? Because V3 is strictly in the span of these first two vectors, V1 and V2. Right? And so you can throw away vector V3 while not altering the dimension of your space or the rank of your space. Does that make sense? Great. And so with this, we kind of have the entire algorithm. Oh, yeah, question?
And what happened to the element after?
So we're just going to keep the elements after. Yeah. We're not going to add them to the basis. We're not going to throw them away. We're just going to keep them, and we'll look at them in a later round. Yeah. Great. So how does the algorithm look at it? Let's zoom out. So we made these groups of size square root n. Within each group, we queried all of the prefixes. And now within each group, either you find square root n independent elements. If so, if you find that in any group, you're happy. You're going to add those to your basis. Otherwise, in every single one of these groups, you found at least one element to delete. And so you're just going to delete that element. Right? And so the key recursion that they show in KUW is that in just one round of these queries, you've reduced basis finding from a matroid on n elements to a matroid on n minus square root n elements. Right? Because you either added square root n elements to your basis, or you threw square root n elements away from your buffer. And does that make sense? Does anyone have any questions? This is kind of, there's a lot of insights happening here, and it's like, showing that there's non-trivial things to be done in this space of parallel basis finding. Question?
Do we repartition the remaining elements into square root groups each time, or do we keep them?
Yeah, we'll repartition it and do it again. Yeah. Yeah, exactly. Perfect. And so now there's a question, right? Can you do better, right? Square root n is already so great. Can you actually beat square root n for this problem? And so again, in the work of KW, they already looked at this question too. And what they showed is that you can't do too much better. Right? They showed that any randomized basis finding algorithm, which even uses poly n queries per round, it must necessarily require at least n to the 1/3 adaptive rounds to find a basis. Right? And so we have this square root n upper bound. We have this n to the 1/3 lower bound. But the complexity can still be somewhere in between these two endpoints. And one thing I want to mention is that this lower bound of n to the 1/3 rounds, it actually holds even for a very basic class of matroids, which were these partition matroids that we saw at the very beginning. And so this naturally frames the question, what is the true parallel complexity of finding matroid bases? Yeah, question?
Do you have any intuition of why that?
Yeah, I'll go through intuition in a couple slides, yeah. Great. Right, so what is this true parallel complexity? And so that's where our work comes into play. And what I'm excited to say is that it turns out that you can actually beat this upper bound. And so even though this upper bound felt very natural, it's like the natural extension of a greedy algorithm to get you square root n rounds, it turns out that you can actually do better with a randomized algorithm. It uses only a polynomial number of independence queries per round, and it'll find you a matroid basis in just O tilde n to the 3/7 many adaptive rounds. Right, so it kind of pretty significantly improves upon square root n. You get it down to 3/7, which I think is like 0.428 or something. Someone can get a calculator. And it shows that there's certainly more non-trivial algorithms to be discovered within the space of parallel basis finding. And then naturally, again, I mentioned that there's these other problems which use basis finding. And so, of course, you'll get better results for those settings as well. And lastly, one thing I want to mention is that these techniques also give you optimal algorithms for this setting of partition matroids. Right, so this lower bound of n to the 1/3 was shown for partition matroids. And we show that you can actually match that in the setting of partition matroids with our improved algorithm. Great. And so for the remainder of the talk, I'm first going to focus actually on this setting of partition matroids, because I think it's the best setting for intuition. It'll show you, at a pretty deep level how the techniques work. And again, time permitting, we'll talk about this second point. But even if we don't get there, the techniques there, they really are inspired by the partition matroid setting. And And it's kind of just messier because the matroids aren't as nice. But so we're really primarily going to focus just on this first point. Great. So yeah, tight bounds for partition matroids. Yeah. I know 4. So this is a bigger number. So, yeah, it's like 444, right? So yeah, it's.
So you're showing
if time permits, I'll show you a worse version which still beats squared n. But again, I don't know if we'll get there with the time. But there's no worry. I think partition matrices are showing you a lot of non-trivial stuff. Perfect. So first, right, we had this lower bound from KUW, which shows that you can't hope to beat n to the 1/3 adaptive rounds. And you asked, can you actually see some intuition for this? And yes, we'll go through some intuition. Where is this lower bound coming from? And so the lower bound here, again, it uses partition matroids. And I defined these at the very beginning, but in case we forgot them, well, you have your ground set E as n elements. You partition it into pieces P1 through Pk. Each part has a budget Bi. And a set is independent if and only if you don't exceed the budget in each one of these parts. And so what exactly is the lower bound instance? It's actually just a very concrete family of matroids. So what we're going to do is we're going to take our elements. Again, there's n elements in the ground set. And we're going to randomly partition them into n to the 1/3 many parts. Right? And because we have n elements and there's n to the 1/3 parts, the size of each part will be n to the 2/3. Right? And the only thing that'll change between these parts is their budgets. Right? So the budget of part I will be I times n to the 1/3. Right? So you kind of have this like staircase of increasing budgets throughout your n to the 1/3 many parts. Right? So that's the class of matroids. It's worth mentioning, right? This isn't just one single matroid, because we're randomly partitioning the elements into the parts. Right? So you have your n elements, and then you randomly permute them when you're deciding which part will they land into. So it's really like a class of some like exponential number of matroids, depending on which element lands in which part. And so the first thing I want to convince you of is that when you think about an algorithm which is trying to find a basis of this matroid, such an algorithm, right, it's making queries of subsets of elements. I claim that any query that you make is really just a random sample of that many elements. These are morally equivalent. And so does that make sense, right? The reason why is that the algorithm doesn't know anything about this random partition of elements that you did. And so when you make a query of elements, it might as well have just been a random query of that many elements because, again, it doesn't know anything about this partition. Great. And so now the key intuition for this lower bound, and what they discussed in KUW, is that with very high probability, whenever you make a query Q to the independence oracle, the answer to that query is governed almost entirely just by its intersection with part P1. Right? And let's see why that's the case. First, let's imagine that your query is big. Right? So imagine that your query was at least 3/2 times n to the 2/3 many elements. What happens then? Well, again, how many parts did we have? OK, we had n to the 1/3 many parts. And so if you do a random sample of this many elements, then with extremely high probability, when you look at just the part P1, you'll have at least n to the 1/3 many elements that land there. Right? In expectation, it's 3/2 times n to the 1/3. And so you'll do some Chernoff bound, and you'll have at least n to the 1/3 elements with an extremely high probability. And right, so in this setting, whenever you make such a query Q, the query will be dependent, right? Because you've exceeded the budget of part P1. But importantly, right, the reason why Q is dependent is because of Q intersect P1. Right? And so this is what I mean when I say the answer to the query is governed by Q intersect P1. Right? Like, sure, the query is dependent, but it's dependent because of what's happening in part P1. Does that make sense? Good. On the other hand, let's imagine that the query is small. Right, so let's imagine that Q has at most 3/2 times n to the 2/3 many elements. the point now is that your query Q does not exceed the budgets of the other parts. And why is that? Okay, there's n to the 1/3 many parts. And so in each part, you expect at most 3/2 times n to the 1/3 many elements to land in them. But the budgets of these parts P2 through Pk are all at least 2 times n to the 1/3. Right? And so you're asking for an extremely unlikely event that, like, this binomial distribution with mean 3/2 times n to the 1/3 anti-concentrates all the way up to 2 times n to the 1/3, right? Which is just extremely unlikely. Right, and so what it's telling you is that all these other pieces, P2 through Pk, are not contributing a dependence. And so whether the query is dependent will depend only on Q intersect P1. Right? It depends only on what's happening inside your first bucket. Does that make sense? Does that give you intuition for the lower bound? Right, so the point is that when you make this first round of queries, it's basically only revealing information about part P1 and very, very little about these other parts P2 through Pk. Right, and now you're just going to iterate the argument. You'll say, in the next round, you're basically only learning information about P2. And then after that, you're only learning information about P3, and so on. Right, and the number of parts that we had in the partition Matroid was n to the 1/3. And so then naturally, this gives you an n to the 1/3 round lower bound for finding a basis of this instance. Perfect. But I claim that, okay, with this example that I just gave you, and at least the kind of rudimentary analysis that I walked you through, there's a very tempting question which arises. And so does anyone have any questions? Maybe you'll have exactly the question I have in mind.
Does it just do it or the up bound too?
Yeah, okay, so I don't know if maybe this is the question you're going for. Why can't you just get a better lower bound? Right? We had these pieces of size n to the 2/3. We had n to the 1/3 many. Why can't you just do square root n of size square root n? Right, where the budgets again are a staircase going from 1 to 2 to 3 to 4 all the way up to square root n. Why doesn't this give you a better lower bound? Is that your question?
I think it's similar.
Similar? Okay, yeah.
And so 1.5 elements.
Oh no, so this is only n elements, right? Because the sizes are square root n, and the budget. Yeah, yeah. Right? Does it make sense? We had this beautiful, in our last example, right? You had the staircase, which said you only learn the first one, you don't learn the second one. So why don't you just do the same thing, but now you break it into square root n of size square root n? Is the question well defined, or do we under? Yeah.
That you don't learn about all of the partitions in one query.
Exactly, right? And so that's the intuition have. It'll turn out that you can't prove that you can, that you can't learn information from multiple pieces at the same time. And so we're actually going to go through this. I'm going to explain to you why you can't get a better lower bound, because this will actually be very important intuition as we go forward with partition matroids. Right, so let's suppose that you have an algorithm which is trying to find a basis of this instance. Right, so you have your square root n parts. Each part is of size square root n. And your budgets have the staircase 1 to 2 to 3 to 4 all the way up to square root n. Right, and let's imagine that you have an algorithm which has learned the first I-1 parts. And so you only have parts pi through p square root n remaining. And so what are we going to do? We're going to make a query Q to the independence oracle such that Q's size is basically I times square root n. And so what do I mean by this? Choose a query such that in expectation, you pick up I elements from each part. Does that make sense? Right? So you want to get basically I elements from pi, I elements from pi plus 1, I elements from pi plus 2. So you're just going to make a random query of basically I times square root n many elements. And so now let's ask a question. You look at any part pj, and then you take your random query q. What is the distribution of this size? What's the distribution of the number of elements you expect to land in part pj? Well, okay, by the above, at the very least, we know the expectation, right? The expectation is I. We kind of like forced it to be I. But importantly, there's a standard deviation of square root I. Right? You expect I elements to land there, but there's this anti-concentration because the standard deviation is square root I. And so in particular, because of this standard deviation of square root I, when you make a random query Q like this, there's an omega-1 probability that in part pi plus square root I, you exceed the budget, right? That you get I plus square root I many elements, while at the same time, in part pi, you don't meet the budget. Right? These are both like omega-1 probability events on their own, and the parts are independent. Right? So there's an omega-1 probability that here you cause a dependence, while in part pi, you don't cause a dependence. And so why is that an issue? Because now it's telling you that the response to your query Q depends on all of these different intersections, right? It depends on part pi, it depends on part pi plus 1, all the way up to part pi plus square root I. And in fact, you can actually turn this into a formal argument. You can show that you can actually learn the identity. And when I say learn the identity, I really mean you learn the budget, you learn which elements are in the part. You can learn all of this for parts pi all the way up to pi plus square root I in just one single round of queries. And so not only is this not a square root n lower bound that you're getting from this instance, but it's actually a much easier instance than the n to the 1/3 round lower bound. Right? What you're learning is that in Q rounds, you can actually recover omega Q squared many parts. And when I say recover, again, I just mean that you learn which elements are in those parts. And so for this instance that we defined, right, the square root n parts of size square root n, you can actually solve the entire instance in just n to the 1/4 many rounds. Yeah, question?
Something I don't understand about this is like the elements that I don't sample, I don't understand how you could like possibly place those in any one of the parts. Or like, yeah.
So you're going to do like tons of these queries at the same time. Like you'll do a polynomial number at the same time.
I see.
Yeah. Yeah. Great. Does that answer your question? Yeah. With just one query, you won't hope to accomplish it. Yeah.
Yeah, you wrote one round and I heard one query.
Oh, okay. Now you're definitely doing a polynomial number in that round. Yeah. Good. Okay, but I promised you an optimal algorithm for all partition matroids, right? Okay. So far, all we've seen is like, okay, you can solve this very basic instance where it's like square root n parts of size square root n and so on, right? But so how do we design algorithms that work on all partition matroids? And so for this, I'm just going to give you a warm-up claim. And I'm not actually going to prove the warm-up claim to you in kind of interest of time. I'm just going to give you the warm-up claim, and then if you have questions about it, you can ask me. But otherwise, we're just going to like kind of black box this warm-up claim. And so that claim is that you're given a partition matroid with these parts P1 through Pk. And I claim that you can recover the identity of some part in just 2 rounds of queries. And when I say recover the identity, what I mean is that you can learn, okay, like this is part P2. These are all of the elements inside part P2. And this is the budget of part P2. Right? So you literally know everything about those elements. And I'll give you a kind of the high level for what this looks like. So let's go through an example where we have a part P1 with budget 1 and 3 elements, and another part P2, again, whose budget is 1 and has 3 elements. And so the way this algorithm will work is that you're going to sample a random permutation pi over the elements. And now you're going to query every prefix of the permutation, kind of similar to what the KUW algorithm was doing. Right, so you take element pi of 1, and you query it to the independence oracle. Right, so in this case, it lands in part P1. The budget is 1, so it's still independent. You take element pi of 2. You query it to the independence oracle. Again, it will turn out that it's independent because it's in part P2. And then you'll keep on, right? You're querying every prefix. Eventually, you'll query, pi of 3 maybe is element 6. And so now the query tells you dependent. Right? So now you have 2 elements in part P2, so the query would be dependent. In the claim, which I'm not going to go exactly into detail on, but it's relatively simple that given a setting like this, you can actually learn what the budget is of part P2, and you can actually learn which elements caused the dependence in part P2. Right, so here it was elements pi of 2 and pi of 3. Turns out there's a very simple way to learn these elements pi of 2 and pi of 3, that they're in the same part, and that they violate the budget of this part P2. And again, once you have this information, you can actually learn all this information about P2, right? You can find all the other elements as well. And I'm not exactly going to prove to you that you can do this, but I hope you can kind of get the intuition that there is this simple procedure, and at least I'm claiming that every time you sample a random permutation, you can learn the identity of whichever part is causing the dependence that arises. Is that all right? And so with that, I can actually now give you, the final algorithm which works for all partition matroids. And so what is the algorithm going to do? It's going to be an iterative algorithm, and it's going to heavily use this algorithm from the previous slide. Right, so in each round of the algorithm, we're going to sample a polynomial number of random permutations. And just as in the previous slide, right, you sampled one random permutation. Now you're going to sample a polynomial number of random permutations. For each one of these random permutations pi, you're going to run that single part recovery algorithm that I mentioned on the previous slide. And right, each time you run this, it'll recover some new part of your partition matroid. We're going to let Si be the union of all of these recovered parts. Right, so every permutation recovers some part. We're going to let Si be the union of all these parts that you learn. And then you're going to remove that set S sub I. And so if S1 through Sk are your recovered sets, right? You ran this iterative algorithm, and you're just asking how many rounds does it run for? In order to prove an n to the 1/3 round upper bound on the algorithm, all you have to show is, again, that the number of rounds is bounded by n to the 1/3. Right, so I'm going to say that k is the number of rounds. I'm just going to show that the algorithm terminates within n to the 1/3 many rounds. Is that good? Right? Because the intuition, again, is that every piece that you recover in Si is some part of your partition matroid. And you've learned everything about that part by the time you've peeled it off. And so the algorithm terminates once the matroid is empty. And by that point, not only have you, found a basis of your matroid, but you've really learned everything there is about the entire partition matroid. You've learned which elements are in which part and with which budget. So you really know everything about it. Great. And so the challenge here is that since each Si is a union of parts, we actually need a more robust notion of the budget in order to argue that we're making progress as you go from S1 to S2 to S3 and so on. And so for this, the key notion that we introduce is this parameter called alpha of S. And there's 3 minutes left, or what's the time? 2 minutes, or 2 minutes? OK.
We have a
So-
little until
No, I'm not going to go over time. So we'll just do 2 minutes, and then I'll conclude. Great. So this notion is probably like the most key contribution. So it's something called the circuit trigger parameter. Again, what is it? You have a matroid. Again, you have your ground set E. You have your independent sets I. And you're looking at some subset S of the elements in this matroid. And this alpha parameter, again, you have to think about this random permutation experiment. So you sample a random permutation over the elements of your matroid. And now you query every prefix of this random permutation. Right, so you query pi of 1, you query pi of 1 and pi of 2, pi of 1, pi of 2, pi of 3, and so on. This alpha parameter, it's just the median index L where dependence first arises. Right, so again, for each permutation, you can do these prefix queries. Eventually, they'll become dependent. And we're just measuring, okay, how far into the permutation did you get before that permutation arose? We're taking the median across all permutations and calling that alpha. And so informally, alpha is kind of measuring how tight the matroid is, right? If alpha is very small, it's saying when you sample a permutation, that dependence arises quite quickly. When alpha is large, it's saying that you can actually go quite far into a random permutation before that dependence arises. Right, and so as an example, if S is a uniform matroid with budget B, then this alpha value is B plus 1. Right, because your dependence always arises at element B plus 1. And so then this is maybe the slide that I'll end on. And this is really the key fact that we show in the paper. Right, so if you think back to this algorithm on the partition matroid, what was it doing? It was peeling off sets S1, S2, S3, and so on. And the question is, why does this algorithm terminate in only n to the 1/3 many rounds? And the answer is that the alpha values of these sets that you peel off satisfy the same recursion that we saw in that example with square root n parts of size square root n. Right, so if you remember there, we had this notion that the budgets increase by like an I plus square root I factor. It turns out that the same recursion holds here with the alpha values of the sets that you peel off. Right, so you get this square root growth condition in your alpha values, and you can use this to show that your algorithm will terminate in just n to the 1/3 many rounds. And again, I think we're up on time, so maybe I'll end it with that. And you can feel free to ask me for any more details.
Any other questions for Louie?
Yeah, question?
What's known about the parallel complexity of matroid intersection?
So it's also sublinear. I think it's like it uses matroid basis finding. And so I think the state of the art right now is like n to the 37 over 45. But yeah, whenever you improve basis finding, like it improves the matroid intersection. So like there's some tug of war. Yeah. Good.
Do any cases any like max weight basis?
These should work for max weight basis also. One way to see it is that this lets you compute the rank. Right? It's saying like, one round of rank queries is worth like n to the 3 over 7 rounds of independence queries. And I think with rank oracle, you should be able to find a max weight basis in just like one round. And so it should work, yeah. Yeah, question?
Does into the 3/7 feel correct as
No. In particular, so again, we didn't get to the general matroid stuff, it's very similar to this. Right, so what are we showing here? Again, I don't know if there's maybe, like basically you're showing that there's this square root growth. And this necessarily implies that the decomposition runs for at most n to the 1/3 rounds, right, this peeling process. The same statement is true for general matroids, right, that you can peel these sets, it runs for n to the 1/3 many rounds. It's just that like these pieces that you peel off, they don't look as nice as partition matroids. And so you can't do as much with the decomposition, or at least we can't prove that you can do as much. But we think you actually can. And so we actually think the right answer is n to the 1/3. We just don't know how to show it.